Hey everyone, so in this video we want to talk about grains. And grains is basically an advanced version of particles or pops. And the idea here is mainly that grains allow particles to collide with each other. And this is the idea why it's called grains, because to have a realistic behavior of something like sand, for example, this is actually what feels then like sand when they actually can create a volume. Now you might wonder why pops don't by default collide with each other, and the main reason is actually speed, because as we will see, a collision between so many points that we need to simulate sand or any particle simulation really is really time consuming and needs a lot of calculation time, which you can save if you don't need that. But in our case, we want to have that, and let me show an example of the problem here really, and that is, let me start with a finite amount of sand, let's say. And we want to turn, for example, this sphere into points. We could, scatter into a volume, but there's a quicker way. We know we can use points from volume, for example, to scatter inside of that object. And we can lower the particle separation, let's say, to make, more of them, maybe something like that. And let's put this into a particle simulation with a popnet to save some time, because all we have to add here, everything else is prepared, is gravity. Now our mouse, because we have to change one thing, like I said, we don't want to constantly emit new points. We want this to be a finite amount of points, and then we want just to simulate those. So we can get rid of the pop source and use the initial geometry. And in here we use the great OP input path that is not annoying at all. There we go. And if I press start now, and at least as long as I remember to add with a merge that I set to mutual, to add a ground plane, of course, and now we can do this. Let's press start and see what happens. And the biggest problem here, let's play in real time, is, as you can see, first of all, the points are bouncing around, so let's fix that quickly. In the popnet, under physical, we turn down the bounce. And you can see now, this looks really unnatural. This amount of, something, we would not expect to implode into this tiny thin area. And of course, this is happening because the points are not colliding with each other, so they don't keep a volume. To activate this function, so to say, we actually can look for grains in the menu, and we'll then find pop grains. And when you look at the connections, you can actually connect it up here, and usually you do connect it to sources. And this means when you have a pop source, for example, that it usually comes between the pop source and the solver. But in our case, we don't need a pop source, so it looks like this. And here again, you can see the nature of pops. It's not really a constant stream of data, it's more like a blueprint, because those pop grains will now influence the behavior of our points in the pop object, even though they're not directly connected. So let's see what happens if I press start. And that was weird. So first it falls down and then it kind of flies away in all directions. What's going on? Well, of course, something is missing here. And as we said, the points are now able to collide with each other, but if they are supposed to do that, they need to know how big they are. Actually, they do know, because in the pop grains, there is a particle separation, which is 0.1, which is actually pretty big. So if we would create a sphere here with a scale of 0.1, then each point currently has this size, basically. And this is actually why they're exploding, because they're colliding with each other. Now, you could, of course, change it in here, but you can also actually change it, and that's more common, by setting the p-scale outside. And if you do that, and let's try something smaller like 003 or something, and see what happens. And you can already see something interesting happens. The starting frame is already different, and if I run this, it explodes, but it explodes in a more reasonable way. And simply that's because the p-scale is now smaller, but it's still bigger than the actual distance was that came from the points from volume. So as you can see, it's really hard to guess what the distance is, but actually you could calculate it because it's always the half of the point separation. But here's the good news, you don't have to do this, because there's already a node called grain source that does all that for you. I just wanted to show you that basically this is the same thing, just as a preset, because it has the same settings as the points from volume with the point separation, which we can use here as well. And the good thing about it is it automatically calculates the right p-scale for us, as you can see here. And of course, what you can imagine, because it has a little lock here, this is actually an asset. So if we go in, this is actually a preset from side effects. And if you look long enough, you will sooner or later find the points from volume in here that is actually doing the exact same thing as we did before. So this is nice. This saves a lot of work and prepares everything for you exactly how the grain system expects. But you can always do it yourself if you really need to. Now let's have a look what happens if I run this now. Now the distance between the points is actually correct, and you can see they don't collide anymore in the beginning, so there's no collision in the beginning. And also when they fall down and collide with the ground, it looks all of a sudden much more realistic. But there's still something odd, and that is this weird noise and this moving around, especially at the end, some stop and some still move. This is kind of weird. It almost feels as if they are alive. And this is actually really important to understand what's happening here. And that is that the points are not calculating their collision all at the same time. So what's happening instead, this is actually calculated one point at a time, so to say. And this is why you actually have to increase the steps that are calculated for each frame to a much higher number whenever you work with grain. So if we go into the POPNet in the POP solver, we have to increase the min and max substeps, because in this case we want to make sure we overwrite whatever automatic number will result. So this is why you give it the same number for min and max. And let's try 10, for example. And if I run this now, of course it's much slower. But when you look at the result, it looks much more natural and way less erratic. And again, the reason for this is that basically the points cannot be calculated at the same time. They can only be calculated one at a time. And this is why you need, for example, 10 substeps to calculate all the different collisions between certain points correctly. Let me actually explain this to you in a little graphic. So to understand how grains work, we have to understand that this is actually a system that is called PBD. So that's the technical term for this system. So you might find a PBD system in other contexts, maybe in other 3D programs, and maybe it's not called grain then, but the technical term of this is PBD, and that stands for position-based dynamics. Because the way to calculate something like that, developers actually originally, many years ago, tried to calculate this with an actual collision calculation. So basically, velocities and all that. So whenever something hits something else, it's pushed away and it gets a new velocity and all that. But the problem with that is it becomes very unstable, and things tend to explode by themselves and energy is accumulated. Imagine like a crowd of people that is moving around, it never settles and it doesn't really feel like sand. It will behave a bit more like fluids or something. So they come up with a better idea, and instead of actually calculating velocities, all they correct basically is positions. And this is why it's called a position-based dynamic system. So instead of a particle pushing something away, it's actually, as soon as there is a collision noticed, it just corrects the new position of the point without adding any kind of velocity to it. And this is what we see here. And the way to imagine this is a little bit like those 80s toys that you sometimes saw on the desk of a villain or something. It's called a Newton pendulum or Newton's cradle, and this could be a good example of understanding how a PBD system works. So let's imagine the first ball arrives here from the right and gets in contact with the first other ball and stops. And then the system notices, oh, there is a collision. So what it does, it takes the second ball and corrects its position so that there's no collision happening anymore. So it pushes it to the left. Now this is calculation that happened on the first subframe. This subframe is now done, and the new situation we have in subframe 2 is this. Now in the second subframe, the PBD system recognizes a new collision and it does the same thing again. Oh, it realizes there's a collision with a third ball, so it corrects the ball by moving it to the left, and so on and so on. So in this case, it takes 5 collision steps to kind of finish this situation so that there's no collision left. And what you can see here, the rough rule that you can keep in mind is that the amount of subframes you would need to calculate the correct collisions is actually the longest possible chain of collisions that can happen, roughly speaking. And this is the reason why we have to increase the sub-steps, so that every step can actually help to come to the right end conclusion. So this is why in our example here, we changed the sub-steps to 10. Now, is that correct? If we look at the ball, we can, if we would actually count this, probably the longest possible chain is longer than 10. And this is why increasing this number would actually increase the precision of this. And if we run this now with 30, let's say, we would probably get a better result. Now, of course, it doesn't mean you have to always put in the exact same number as your longest chain, but just in theory, that would be correct. In practical terms, of course, nobody does that. What you always try to find is a balance between accuracy and speed, and find, the middle ground where you get the best of both worlds. And in a case like this looks reasonably fine. There's nothing that I can see that would tell me that the 30 might be too low. But there are certain phenomena that you can see where the amount of sub-steps is too low. And that is usually when you see some grain simulations that fall together and then they correct themselves too late, basically, which results in a delayed kind of explosion. And I have a couple of examples here for this effect. And of course, this is not to discredit the work of the artist. This is actually a great shot. It's just interesting to see the best and the worst of grain, because it's a well done shot, but it still has this interesting problem at the end. And we see this here. So it breaks apart, and we will actually look at a way of doing the exact same thing. And then when the whole thing collapses, there is a big bounce at the end. You saw that? So this bounce here, you might have not noticed it, but as an FXTD, when you know that there's a grain system behind that, you know what's happening here. This is actually the sub-steps being too low for the whole amount of points at the end, and then it corrects itself too late, which results in a bounce explosion. Here's another example of the same effect, a classical case of a delayed explosion, this time even much higher. So I assume the amount of points is higher, while the sub-steps were even lower than before in the other example. And this is where you see the effect even stronger. So now that you know that, you might, be able to spot these kind of problems. And I guess what's nice is if you don't know that this is actually a mistake, you could sell it as an effect or something. But technically you can avoid this by increasing the sub-steps to a very high number, which of course will slow down your simulation. And if we go back with our sub-steps to 1, let's say, we can actually now better understand what was happening here. This is why there is this crazy movement, and there are a few points that are, at the end moving and the rest is not. Those are the points that are the last that are calculated, and once they are done, they finish as well, but it happens every full frame, so you can actually see the calculation steps. Let's finish this by talking about the physical properties in the pop object. One thing to keep in mind, which is very important, as soon as you use pop grains, those physical properties will not be used anymore. They are completely ignored. So I can set the bounce to 1 and maybe the bounce forward to 0, and I will not see any difference in the behavior to before. Let's now turn this around again with bounce forward to 1 and bounce to 0, and it will look exactly the same. So those are completely ignored. This means when you want to control, for example, the sliding of the points, this is actually something you have to do in the pop grains. And we will look at ways of doing this in another video. It's about those two here in friction. But also keep in mind that there's actually no way to activate bounce in a grain simulation. So if for some reason you need a bouncy grain simulation, this will not work. And the reason is, if you think about it, since there is no calculation of velocities, but only the correction of positions, there is no concept of bounce possible anymore. And this is just something to keep in mind. You can't make a grain simulation bounce. If you want to do something like that, you have to fake it in, I would think. So you have to set some velocities yourself, but the system will not calculate any for you in a PBD based system. So yeah, those are the basics and the core concept of a grain or PBD system. And for this, you need a pop grains node and make sure that your points are positioned in a way that they have a certain distance, and that distance is represented in a p-scale attribute. And this is something the grain source can do for you automatically. And then, very important, make sure that in your pop solver you need a lot of sub-steps, because every step is calculating one part of a collision chain. So the number has to be surprisingly high. And in the next couple of videos, we will talk about how to control this thing a little bit more, and also how to make it more look like here, like small little spheres and not just points. So for now, I hope this is helpful. Thanks very much and see you later. Cheers.